Hi folks, today I'm bringing you a proof of concept that is a bit different from what I usually do on this channel. It was suggested by one of the channel subscribers and I felt it was interesting enough to share instead of leaving it stored away. In this video we are going to look at the M62445, which is a digital sound controller with dynamic bass boost. This integrated circuit supports 5 audio inputs and 1 audio output. The controls for treble, bass, gain and volume all act directly on the output signal. The device also includes a microphone input with predefined modes for karaoke operation, and it provides a dedicated recording output. This is a dual-channel device, left and right, which means it fully supports stereo audio and allows independent volume adjustment for each channel. In addition to the audio features, the integrated circuit offers 2 groups of 4 open collector outputs using NPN transistors. These outputs can be used, for example, to drive indicator lights that show which input is active and which options are currently enabled. There is also an additional group of 2 outputs that supports 3 different status signals. Because there are 2 groups of 4 outputs, we decided to configure the first group to count from 0 up to 15 using hexadecimal representation. The second group was configured to count from 1 up to 8 using binary weighting. All communication with the device is performed by sending 4 groups of 17 bits. This communication uses a data line with clock, data and latch signals. It is important to pay attention to the way the latch signal is used. The latch is activated once every group of 17 bits. The datasheet includes a specific note warning about the correct usage of this signal, and it should not be ignored. The display used in this project has an address of 0x3f, and it receives data through the I2C bus of the Arduino, using the SCL and SDA lines. The M62445 comes in a surface mount QFP package with 64 pins, arranged as 16 pins on each side. This type of package discourages many enthusiasts, since it requires the design of a dedicated printed circuit board. That concern is completely understandable. As is often the case on this channel, we work around this limitation by using a small adapter board. This board mirrors all the pins of the integrated circuit onto the breadboard, allowing direct pin-by-pin access. At this point, it is important to be clear about one thing. This setup is not suitable for high-quality audio applications. Proper audio design would require coaxial cables for each audio signal, or a carefully designed printed circuit board layout to minimize electromagnetic interference. Those rules are clearly not being followed here. This project is strictly a functional test and a proof of concept. I usually try to keep the code as simple as possible and avoid external libraries whenever I can. In this case, however, the problem becomes slightly more complex. We use independent functions that work together, allowing control at the bit level so that the behavior of the device can be clearly observed. I will explain the design choices made in the code, including why global variables were used, even though that approach is normally discouraged. The main objective here is clarity. We intentionally avoid adding unnecessary complexity with pointers or enumerations. One of the first design choices was the use of an unsigned 16-bit variable. This variable is used to hold the 15 bits sent by the function called sendWithoutLatch. To complete the transmission, another function is used, which sends only the final 3 bits responsible for the selection slot. In both cases, bit masks are applied to ensure that only the intended bits are transmitted. It would have been possible to use a 32-bit variable to hold all 18 bits at once. However, because the protocol mixes fields of 4 bits, 3 bits, 2 bits, and even single-bit values, that approach becomes harder to read and harder to understand. Using a 16-bit variable turned out to be a simpler and clearer solution. As an example, consider the command identified by the letter C. In this case, 2 bytes are transmitted. Bits from D0 to D6 control the volume of the left audio channel. Bit D7 is permanently set to 1. Bits from D8 to D14 control the volume of the right audio channel. The transmission is completed with 3 bits corresponding to the selection slot. The intention was not to overload the code with protection mechanisms. However, in a few situations, simple conditional statements were added to make the use of rotary encoders easier within the menu system. As examples, control was implemented for volume, gain, bass, treble, channel selection, karaoke mode, outputs 1 through 4, outputs 5 and 6, and outputs 7 through 10. With these examples in place, it becomes straightforward to add additional options to the menu if needed. To keep everything at a low level, 2 independent power amplifiers were used, both based on the TDA2030 way. Care was taken to power these amplifiers using a symmetrical supply. The M62445 itself is also powered using a symmetrical supply, providing plus 4.75 volts and minus 4.75 volts direct current. The power-up sequence is extremely important in this case. The negative voltage must be applied first, and only then should the positive voltage be applied. If this order is not respected, the integrated circuit has a tendency to enter an overload condition. To safely handle this requirement, 2 low dropout regulators were used, namely the LM7805 and the LM7905, assisted by 2 transistors. The integrated circuit consumes approximately 20 mA on the positive supply rail and 20 mA on the negative supply rail. The liquid crystal display adds an additional current consumption of roughly 20 mA to the supply. Both the analog supply voltage and the digital supply voltage are powered at plus 4.75 volts, while the negative supply voltage is powered at minus 4.75 volts. One of the voltage drops is caused by the transistor used as a switching element. The other voltage drop is caused by the diode inserted on the negative supply rail. Finally, ground 1, ground 2, and all audio ground connections were tied together. This ensures a single common reference point for the entire circuit.